Okay, so now let's talk about math. So last time where we ended was we were talking about uniform convergence. So we said that our goal for the next few lectures will be the so-called uniform convergence, which means that you want to somewhat prove that with high probability, if you take sup or maximum, I guess sup really just means maximum for this course. So if you take sup over the hypothesis class and you look at the difference between the empirical risk and the population risk, you want to show that this is small in most of the, like with high probability. So this is the general idea. And we said that this is different from showing that, so this is different from showing for every fixed h with high probability, L hat h minus LH is small. So these two are of different nature because one, so the order of the quantifier in some sense is different. So one requires that if this event, so with higher probability, the event that the entire population risk is close to the empirical risk, right? So the other one is saying that you just only look at one single h and you look at what's the probability that this population risk is different from empirical risk, and you want to show that this event happens with high probability. So in some sense, the difference is kind of like a union bound in some sense, which I'm going to talk more next when we get to prove this kind of like statement. So so this is the, and in this lecture, we're going to talk about two ways to do this. Actually, we're going to talk about two cases about h, right? So certainly this statement depends on h. You cannot hope to prove things like this for every possible capital H. It does depend on the family of hypotheses you think about, and the bound actually depends on the family of hypotheses you're talking about. So the first part is going to be about finite hypothesis class, where H is assumed to be finite. So finite. And the next part is going to be infinite case, infinite hypothesis class. And for infinite hypothesis class, there are many different ways to bound to achieve this kind of bound. And today we're going to talk about a relatively brute force way to do it. In some sense, you do a reduction to the finite hypothesis class. Essentially no matter what you do, you are doing a reduction to the finite hypothesis class. But how do you reduce to the finite case, does matter. So in today, we're going to talk about the brute force reduction, which does show some kind of intuition. Okay, so that's a brief overview of what we're going to do this in this lecture. So so I guess let me just start by let's talk about the finite hypothesis. And here's the theorem we're going to prove. So there are some conditions. So the condition is as we did last time. Recall that last time we assumed the loss is between 0 and 1 for every xy and every hypothesis. And this is true for binary loss. It's 0, 1 loss. It's not true for every possible losses, but if you have other losses, you have to do a little bit small kind of like fix to make this proof still work. But this is not very essential. It's mostly for convenience. And what we want to prove is the following statement. So we say that for every delta between 0 and a half, this is not very important either. So delta is a small number. And you say that with probability, at least 1 minus delta, we have that for every h, L hat h minus LH in absolute value is bounded by square root ln the size of h plus ln 2 over delta over 2n. And recall that the reason why we care about this kind of uniform convergence was that it's useful for us to bound the excess risk, right? So we have shown that if you have this kind of uniform convergence, then you can prove that your excess risk is bounded. So using what we have discussed last time as a corollary, we also get L, the excess risk of LH hat. H hat is the ERM minus LH star. So this is the ERM solution. LH hat minus LH star is less than you pay a factor 2 in that derivation. So you multiply the factor 2, so you get something like 2 times ln size of h plus ln 2 over delta over n. Okay, cool. So all right. So this is the theorem we're going to prove. And maybe just before we prove the theorem, you can see that the bound, the right-hand side of the bound, does depend on the size of the hypothesis class, right? If you have a bigger hypothesis class, then your bound would be worse. So it's harder to prove this uniform convergence when you have a larger hypothesis class. And if you try to interpret this bound at the end, right? So here, this is bounded excess risk, and we can see that you need n to be bigger than the log of the size of h, so that the right-hand side of the bound becomes meaningful, right? So you want the excess risk to be something smaller than 1 at least, right? At the minimum, so you need n to be at least larger than log of the size of the hypothesis class. So that's why you need enough samples, right, to make this bound meaningful. And of course, as n goes to infinity, you have better and better bound. I'm going to have a little bit more discussion after we prove the theorem. Okay, so now let's try to prove the theorem. So I guess the outline of the proof is that first you do individual h. You prove this for individual h. You prove the simple version, basically like we discussed the last time. And second, we take a union bound over all h. Okay, so let's do the first step. So recall that last time we have done this already for fixed theta, right? So here I'm just doing it a little bit more formally. So last time we actually showed this, right? We used this Hopf inequality to get something like L hat theta minus L theta. This is something like on the order of 1 over square root n. That's what we did somewhat informally last time with Hopf inequality. And today I'm going to have a little more kind of like careful derivations to get exactly all the dependencies up to constant. And by the way, theta and h are the same. H is just when you talk about finite hypothesis class, right? You don't necessarily have a parameter. You may just list all the hypotheses. That's why it's called h. And when you parameterize it, you have the parameter theta. So, but for this purpose, they're not different at all. So let's apply. This is the last lecture. So let's apply Hopf inequality. So where AI is 0, BI is 1. So the bound is 0 and 1, right? So we get that for every h in H, right? So suppose this H is fixed, and then you draw your sample, you look at the probability that L hat H minus LH is less than epsilon. And here what's random? The random is the data set. The randomness comes from the data set, which goes into L hat. And if you use the Hopf inequality, you get this is larger than 1 minus 2 times exponential minus 2n squared epsilon squared over sum of beta I bi minus ai squared. And because bi is 1 and ai is 0, so the sum of bi minus ai squared is n. So you get 1 minus 2 exponential minus 2n epsilon squared. And right, this is because bi is 1 and ai is 0. And so in other words, if you look at the other side of the bound, you look at what's the chance that they are different. The chance that they are different is less than 2 times exponential 2n minus epsilon squared. Actually, in many cases, half the inequality was stated in this way instead of the way that I showed before. Right, they are exactly the same. It's just complementary of each other. Right, you have a lower bound for some event, then you have the upper bound for the complementary of the event. So, and now this is for every age you have this, right? So basically for every age you have some kind of failure event, which is this event, and this event happens with a small probability. And now let's recall that you have the so-called union bound. And the union bound is saying that if you look at the union of a bunch of events, maybe let's say k event, then they are smaller than the probability of the sum of the probability of each event. And here, suppose you say the EH corresponds to the event that L hat H is different from LH by epsilon. Then you know that the probability that the union of the EIs, which is basically saying that what's the union of this failure event, basically means that there exists H such that this event happens, right? So such that LH minus LH, L hat H minus LH is larger than epsilon. So this is the union of all of these events, and is less than the sum of each of the events. Okay, so and now you plug in what you have prepared. Maybe let's say this equation, let's call it 1. So if you plug in 1, then you get this is sum over all the h's, and you get 2 times exponential minus 2n epsilon squared. So each of these events is small, and you multiply by the total number of the possible events, which is the size of h. So basically, you have 2 times h times exponential minus 2n epsilon squared. Okay. So, and you can see that this is basically what we wanted to have, because now we have there exists h such that this such that they are different. So the complementary of this will be just that this is just equals to 1 minus the probability that for every h, the flipped event is true. Right. So, by the way, I'm not distinguishing the larger to equal or like in most of this course, like so technically I probably should write this is less than epsilon, right? Instead of like less than or equal to epsilon. But you know, for this part, for this course, like I'm not super careful about this because they don't really matter that much. And in many cases, actually, the probability that you actually this is exactly equal to epsilon is actually 0. So technically they are even correct. But anyway, so this is not super important for this course. But right when you so because of this, you can see that this is what we care about, right? For every h, L hat h is close to LH, and we are already kind of getting there almost, right? So the only thing we need is to know what this quantity is, right? We need to upper bound this so that we can lower bound this probability. Okay, so now let's choose epsilon, right? So that you can get so basically you want this probability to happen. You want this thing to be bigger than 1 minus delta. So that's why you want this to be less than delta, right? So so basically we just need to choose epsilon so that this probability becomes delta. So choose epsilon such that 2h times exponential minus 2n epsilon squared is equal to delta. And this involves you solve the equation, you know, which is not too hard. So if you solve it, you get epsilon is equals to, I guess exactly what I had before. So epsilon is equals to ln h plus ln 2 over delta over n over 2n. So basically, if you take epsilon to be this, then you know that the probability that for every h, L has h minus, maybe let's start with the existence. LH is bigger than epsilon. It's less than less than delta, right? So, and then if you flip the event, you get the desired theorem. Any questions so far? Okay, so let me have a few remarks to kind of somewhat interpret what we have done and compare it with what we did in the first lecture. So if you compare with the asymptotic result, you're going to see this, right? So for asymptotic result, what you got is that LH hat minus LH star, right? The excess risk is bounded by, is something like C over N plus 8 of 1 over N. And recall that this C, can depend on dimension or the problem. And here you can hide any other dependencies on the problem. So, and what we have now is that LH hat, the excess risk minus the, LH hat, not L hat. The excess risk is smaller than, so here you don't hide anything. You hide some constant, of course. You hide this is ln h over n over, square root this. And of course, you also have something like of square root ln 1 over delta over n. So this term is supposed to be relatively small because you can take delta to be, this is logarithmic, right? You can take delta to be something like maybe n to the 10, right? So you still get log n over square root log n over square root n, right? So let's say take delta to be n to the minus 10. So then this one will be square root log n over square root n, which is negligible, or almost negligible compared to the first term. So, so basically, let's say we ignore this for the comparison. So ignore this for the comparison, then you can compare this and this. So you can see that the first thing is that we have a worse dependency on n, right? Before the dependency, at least for the leading term, at least in terms of leading term, the dependency on n was 1 over n, and now it's 1 over square root n, so it goes to 0 slower. So however, there's no so this could be improved. This can be improved in certain cases, which we probably wouldn't do at all. I guess in one of the homework questions, you're going to be asked to improve this to some extent. In some cases, you can improve this to 1 over n, depending on various situations. But generally, I guess you get relatively worse dependency on n in compared to asymptotics. And one of the reasons why this is one of the reasons why this is happening is that so partly because we didn't assume twice differentiability. Loss function, right? So here our loss function is only the only assumption we have on loss function is between 0 and 1. So it even works for like 0, 1 loss, the classification 0, 1 loss. But before, we did assume that the loss has to be continuous and differentiable, and I think we also assume it's twice differentiable. So that does play a fundamental role here. So when you don't have twice differentiability, and when you don't have other assumptions, it's very hard to, it's kind of like actually impossible to get 1 over n rate in many cases. So, but here, what I'm talking here is all about the downside of our new bound. So the pros, we actually already kind of like mentioned. The main pro is that now we don't have any dependencies about anything, right? So before, recall that last time when we motivated to have non-asymptotic bounds, we are saying that this thing could hide a lot of things, right? This could hide, for example, something like dimension to the 50. That's my extreme example, over n squared, right? So p to the 50 over n squared will be counted as late of 1 over n, right? So that doesn't make a lot of sense, just because if a dimension is too high, then this requires n to be very big to be small, right? So this was the issue that we mentioned last time about asymptotics, and now we fixed that issue, and that's the main benefit we gain, right? So we don't have anything about the dependencies, and also we explicitly see what's the how does this depend on the complexity in some sense of the hypothesis class. You can think of this as a complexity. The log h can be think of as a complexity of the hypothesis class. So I guess probably if you have been to CS229, we have talked about, if you can overfit if you have too complex a function class, but you don't have enough data. And this is, in some sense, a mathematical characterization of that, right? So if your function class is too complex, so that the log of h is too big, and you don't have enough data compared to log of h, then you may have a worse bound. And on the other hand, suppose your log of h is small and your n is bigger than log of h, then you have a better bound, which could be meaningful. Okay, any questions so far?
How does the reversibility come into play here? We're doing with the finite set.
We are doing, yes, no, this is the differentiability of the loss function. So the loss function is a function of, depending on how you think about it, but by the differentiability, I really mean this function that takes in y hat and y, and output the scalar. So you take in the prediction and the real label, and you output the scalar. So whether this function is differentiable with respect to y and y hat. So we didn't assume that this function is differentiable here, but implicitly you are assuming that this loss function is differentiable with respect to y and y hat in the previous asymptotic analysis, because there actually we assume the whole loss function, even you compose it with the model, has to be differentiable.
Or like practical implementation of floating point numbers, you could use a similar bound.
So I didn't hear very
well. Practical implementation of floating point numbers, can you use like the same bound?
For practical implementations where you have floating points?
Yeah, and then so you have just 64 possible floating point numbers, and data numbers that you have to use
So I guess my interpretation of the question, maybe let me rephrase the question a little bit, also for the Zoom people on the Zoom meeting. So I think the proposal is that, for example, if you really have a practical model and you have like a p parameters, and they are, when you really implement this in computer, it's not continuous, right? So you can think of like each parameter is described by, maybe 32 bits, and then you can count how many total possible number of different models there are and apply this bound, right? So yes, and that's a good idea, and that will give you what? That will give you that, suppose you have p parameters. let's say you have 32 bits. So 1 bit is, so then what does it mean? That means that the total size of H would be that for every P parameter, you have 2 to the 32 choices, and you multiply that to P, right? So you take the raised power to P, and so that means the log of H is equals to something like 32, like O of P, right? It's a constant times P. So basically, you're gonna get a bound that depends on number of parameters. And this is reasonable in some cases. This is not very reasonable in some other cases, but definitely it's a bound that makes sense, right? So in some of the later part of the lecture, we are going to see how to get a bound that doesn't depend on parameter. But if you are fine with getting a bound that depends on number of parameters, then this is indeed a good bound. And this is actually a natural question that leads me to the second part of the lecture, today's lecture. So this is a proposal where the proposal to do this has a small cons or a small kind of problem, which is you basically have to say that I have to resort to practical implementation. In practice, I cannot really implement real numbers, right? All the real numbers. I have to discretize in some way, right? So that's, in some sense, you put a additional restriction on yourself, saying that if I can only use like a floating points, then what bound I can have, right? So what I'm going to discuss now, right next, is that you don't even need this. You can even say that even for all the possible continuous models with it's supposed to have P parameters, and each parameter is really a real number. Like you can, for example, suppose you have an almighty computer which can have like infinite precision. Still, your bound would still look like something like this. You still have an O of P bound, like so then you don't have to, like, suppose we have that infinite like hypothesis class proof, then you don't need this practical this way of proving it, right? You can have a more general and stronger way to prove it, and that's what we're going to show. Okay, cool. So okay, so maybe let's start to do that. So let's talk about infinite hypothesis class. And as I suggested, a little bit before, so we are gonna have a bound that looks like P over n square root P over n, and P is the number of parameters. So this is something we're gonna have. Okay, cool. So so today we're gonna do this so-called like a brute force discretization. This is a technique, or at least this is how I name this technique. I guess because this technique is too brute force, I guess there's no really real name for it. What you can do is the following. So yeah, let me state the theorem that I'm going to prove first, and then I can tell you what's the intuition and how to prove it. So this is a theorem. So suppose H is, okay, I guess I'm still setting up. Suppose H is parameterized by theta in P dimension. So H is, mathematically you write H is a family of H sub theta. Each H sub theta is a parameterized model, where theta is in some set of theta, which is a subset of RP. So capital theta is the set of parameters you are going to choose from. And in some sense, this is for convenience. So, but I guess you probably wouldn't see why this is only for convenience, but doesn't really matter. So suppose you only select models from this set, where your norm of the model is bounded by B. Our dependency on B will be only logarithmic. So in some sense, this is not really a real restriction, right? You can choose B to be pretty big, just because your dependency on B is very relaxed, right? It's logarithmic in B. So this is our setup, and also let's recall that we sometimes going to use this notation. This is really, we use all of these notations interchangeably. So either this is really just the loss of theta, the model theta on the data point x and y. So it's really just you compare h theta of x and y, and you get a loss right? These two are just the same thing. Like we are abusing notation a little bit. And also recall that we have L theta, L high theta. This is all as we defined before. And so here's the theorem. So we still have to assume that the loss is between 0 and 1. This is probably always assumed in most of this lecture, most of this course, for every x, y, and theta. And suppose this is an additional assumption where you assume that this loss function is k Lipschitz in theta. So so for every x and y. So what does this really mean? This really means that you're assuming L of xy theta minus L of xy at theta prime. If you change your model to theta prime, then your loss wouldn't be differed by a constant times theta minus theta prime in 2 norm. So maybe let's try to. This is kappa. So okay. So again, this our dependency on kappa will also be logarithmic. So in some sense, this is also not assuming much, like because if your loss is kind of somewhat continuous, then you can have it's going to be Lipschitz, to some extent, right? It's probably the Lipschitz constant is not very good, but the Lipschitz constant would be something reasonable. And if you take logarithmic of it, it's not very sensitive to the Lipschitz constant. And then with this, then you get with probability at least 1 minus I guess of e to the minus p. So actually you have even higher, even lower failure probability. The failure probability is e to the minus p. So with so small failure probability, you get that for every theta, you have the uniform convergence is less than some big O of square root p over n times max 1 and ln kappa b and n. So eventually, the dependency on kappa and b are logarithmic. That's what I promised. And the main thing is really p over n. So you get the parameter dependency and you get the dependency on n. And you still have the square root here. So this is still worse than the asymptotic bound if you compare with the leading term of the asymptotic bound. But as we said, you don't have the second order term in the asymptotic bound. Okay, so how do we prove this? So actually, the proof is very similar to what was suggested in the question. So you are doing a discretization, and then you deal with the discretization error separately. So what you do is the following. So let me start with a kind of a sketch in some sense. So the kind of the alternate sketch is the following. So you define E theta be the event that you have this failure event, right? L high theta minus L theta is larger than epsilon. And epsilon is going to be something TBD, but epsilon would be very similar to this thing, right? Because you care about whether these two are different, right? How like this much different. But anyway, so epsilon is some number that is kind of like a placeholder. So you care about this kind of event. And we know that this will be a small probability event, right? As we have shown for the finite case, right? So this E theta is a small probability event. And before, recall that what we did is that we say that the union of this E theta is less than the sum of the E theta, the probability of E theta. But now, because you have infinite number of theta, this is infinite, because each one has some small probability event, right? So to fail, and you take the sum over all possible events, then you get an infinite number. At least, like each of these will be some epsilon, and you take the sum of infinite number of things, you get infinite. So that's why it doesn't work. right? You cannot use exactly the same thing as before. So, but the reason why this is this can be fixed is because this union bound is very pessimistic. So if you think about union bound, right? So union bound is really just saying that, okay, I guess I'm not sure, like depending on how you learn union bounds, you know, in previous lectures, like what I learned about union bound is this following. For example, you have this is the full probability space, and each event takes some part of space. Maybe this is E theta 1, this is E1, and this is maybe E2. And the optimal, when the union bound would be tight, it's when all of this event, they call them failure events, all of them are disjoint, right? So, right, suppose this is the case, then the union of these events will be the sum of the probability of each of the events. But here, it's not clear whether these events are disjoint, and actually they may have a lot of overlap, right? So you have one theta, right? So E theta, and if you change your theta to your nearby theta, you probably have something like this, which is E theta prime, and they have all of this overlap, and then your union bound starts to be very loose. So that's also kind of motivates our way to fix it. The way that we fix it is the following. So we fix it by first picking not all. We don't take union bound over all possible events. We select a subset of events and we take union bound over them, and then we say the other events will be close to some of this subset of prototypical events. So basically the idea is that you the rough idea is that you select prototypical events. Like just maybe I should just say typical events, or you just take some exemplary events. I don't know how to. I forgot how to spell that. Some exemplary events, and this is a subset of events you is a smaller set of events than what you finally care about, and then you use union bound on this subset. And then you say that other events are similar to this subset, to the exemplars. So then you cover all the events. So that's the rough idea. So let's see how we exactly do this. So to exactly do this, we need to introduce something called. Any questions so far? Okay, so to exactly do this, we need to introduce something called discretized epsilon cover. This is actually also a useful tool for other cases as well. So let me first define this epsilon cover and then say why it's kind of like it's a language to describe what are called prototypical events or prototypical kind of like parameters or models. So epsilon net, sometimes it's also called epsilon net, sometimes it's called epsilon cover of a set S, and here S corresponds to the family of all models you care about, and you care about a subset of models. And if you and with respect to, like when you really define it, you have to specify a metric rho. Rho is a set C, which is often a subset of S. But I think technically you don't have to require C to be a subset of S, but I think in almost all cases it's a subset of S, such that for every X in S, right, so there exists a kind of a neighbor in C which is close to X. So if you draw this, it's kind of like you're saying that you have a set of models or parameters. This is called S, and the epsilon cover is a subset of S, right? So as you select some points, and let's call these points, these are all in C, and then you say that this set of C needs to satisfy the following to be an epsilon cover. So what it has to satisfy? It has to satisfy that for every point you pick in S, right? You pick this point X in S, there exists a neighbor, somewhat kind of a neighbor, in C, right? Let's call this X prime. Oops, I guess cross and X seems to be the same. I'm not sure whether, maybe I should, anyway, you see what I mean? Like the purple cross is just indicating a point, but okay. So you have a point X here, and you can always find some other point in C such that X prime is kind of close to X. So that's basically saying that all of these points in C are prototypical kind of points, because every point in S can find a neighbor in C. Does that make sense? And equivalently, you can also write this in the following way. So equivalently, this is in some sense more explaining why this is called epsilon cover. So equivalently, you can write this as the S is covered by the union of the ball around all the X. Let me write it down and explain what this is. So first of all, this thing is the ball centered at X with radius epsilon and distance metric or metric rho. So basically this is saying the following. So this is the equivalent definition of the epsilon cover. So you are saying that if you look at all the balls around all of these purple points, right? So this is the radius is epsilon. So in some sense, you can say that this ball, so this point covers the entire ball, because for every point in this ball, you can use this point, the center, as the neighbor, right? So basically every point covers some part of the space. And so the requirement is that if you look at all the points that can, if you look at all the balls around all the centers, then this should cover the entire S, right? That means that every point in S can be covered by some ball. And that means every point in S has a neighbor in C. Any questions? Okay. C might not be. We will, in some sense, we will insist that C, we will need to find a very small cover C, which is finite, and also hopefully we want the size of C to be small. But by the definition, there's nothing about whether it's finite or not. But we will construct epsilon cover that is finite. Right. So this is so far this is only a definition saying that C is epsilon cover of S. Yeah, but we will try to make C to be small. And this is actually exactly so this is exactly what we're going to do next, right? So how do we construct a set C that is finite and also cover the entire set, right? So what is S, right? So for us, S is the set of all parameters, right? It's the set of parameter theta with this L2 norm less than B, right? You want to construct a subset of parameters that can cover all the parameters, right? So here is a lemma that says that you can do this, and you can have finite C, and also actually you can have a reasonable bound on how many points in C there are. So let's define this to be, I guess for this lemma, I call this theta. So theta is defined as above. So for every epsilon in 0 and B, for every radius, there exists an epsilon cover of the set theta, the L2 norm with radius B, such that with at most 3b over epsilon to the power p elements. So this is a cover, and the size of this cover is bounded by 3b over epsilon to the power p. Okay, so I think this is actually we're gonna prove a weaker version. The full we're gonna have a homework question which kind of guide you to prove exactly this version. So for now in the lecture we're gonna prove a weaker version, which is somewhat easier. So this weaker version, and also actually suffices for our purpose, right? So like you don't really necessarily need a stronger version to prove the final theorem, just because this, like the weaker version is only weaker by a little bit. So I guess the homework will guide you towards the stronger version, which also introduce some techniques, which is useful. So here's the weaker version. The weaker version is pretty much like you discretize your computer, right? You just do a trivial discretization using some grade. So what you do is you just take C be a trivial grade in some sense. So what does that mean? It really means that you have this ball. Let me see whether, I guess if you have this ball, and you just say that you take that some arbitrary kind of like a coordinate system, you just take the natural coordinate system, and you discretize your space like this. And then you take all this kind of points as your C, and that's it. So and then the question is just a matter of counting and how fine-grained your grade needs to be. So formally, so C is taken to be all the points X in Rp such that Xi, the coordinate, is multiple, I guess this is K times epsilon over square P. So epsilon over square P is my grade size, and K is the integer multiplied with it for some integer. K, where K is smaller than B squared P over epsilon. And why I have this constraint on K? Because at some point you don't need more points because you don't have to do anything beyond this part, right? It's because, you know, if your K is too big, you already outside S, and there is no point. So, and if you do the calculation, this is the right thing. Right, so now we have to do two things. One thing is we have to see how large C is, and the second thing is we have to prove that this is an epsilon cover. So let's do the first thing. So why this is epsilon cover? This is because if you look at any point X in S, you just round it to the nearest nearest point, right? So when you round it to so you do some rounding. Let's see. I guess when you round it to let's call it X prime, right? Let me not write exactly what the rounding. You know, rounding really just means you take the any vertex in this grid and round it. The nearest, any reasonable nearest, like that's what I mean. Like you just do the trivial rounding. Let's say you round to a smaller number. It doesn't really matter that much. So if you round it, so what you got is that Xi minus Xi prime is less than epsilon over square P, because for every dimension, when you round, you create epsilon over square P error, right? Epsilon over square P is your grid size, and that means that the distance between X and X prime, in the L2 sense, right? Like this is, I guess. Sorry, I think this is. I should mention that the rho L2 norm. The rho. This, yeah, I should have mentioned this. So the metric we are using is rho is L2 norm. Right. So then you look at the L2 norm of these two things, right? So this is the sum of Xi minus Xi prime square, I from 1 to P. And then you bound each coordinate, you get P times epsilon square over P square root, which is epsilon. that's actually why I chose the grid size to be epsilon over square p, just because I want to make it epsilon like that. So this proves that it's an epsilon cover, right? So, and also we can count how large C is. So C is what? C is something to the power P, because for every coordinate, you have a bunch of choices for K. And how many choices for K there are, basically this was here is like K, the absolute value of K is less than B squared P over epsilon, right? So basically you get B squared P over epsilon. And because you can be positive and negative, that's why you multiply 2, and you can also be 0, so you add 1. So that's the total number of choices in C. Right, so, and one comment is that eventually only log C matters, as you see. So log C will be P log 2B squared P over epsilon plus 1. And that's why this weaker version is not super different from the stronger version, because the difference, right? So the stronger version was 3b over epsilon to the power p, and the log becomes p log 3b over epsilon. And if you compare the stronger version with the weaker version, the only thing is different is the square root p in the log. So that's why eventually it doesn't change the bound too much. Okay, cool. So this is our proof for the weaker version of the lemma. And now let's use this lemma and the epsilon cover to prove the final bound, right? So as we kind of like planned, what we do is that we first apply finite hypothesis case. The finite hypothesis analysis to C. And then you say that then you somewhat, so this maybe let's say this is number 1, and then you say that extend 1 to the whole set S. Okay, so now the first step should be trivial because we already proved it, right? So if you want to do I, then basically you got that the first thing is that you do it for every fixed theta in C. Then you have probability of this is larger than epsilon. If you use Hoffman inequality, you get this is, I guess let's call it epsilon tilde, because this epsilon tilde will be tuned to be decided later to make the bound fit. So you get this is 2 times exponential minus 2n epsilon squared. This is by Hoffman. Exactly the same thing as we have done before. And then you take a union bound. You got that probability that for every theta, I guess there exists theta in C such that this is not right, is small. And how small it is, you multiply C with this exponential minus 2n epsilon tilde squared. Okay, so these two steps are exactly as we did. And if you flip this, you get 1 minus probability of the good event happens with high probability. I'm just flipping it. Okay, so now we have to do the second step. How do we extend this to for every theta in S? And so second, and we are basically using the Lipschitzness. And you can see that this is not really anything super clever. It's kind of like a sometimes brute force, right? Okay, so just for some quick preparation, so because Lx theta is kappa Lipschitz, this is kappa Lipschitz. in theta, this implies that L theta and L hat theta are both kappa ellipses. Why? This is just because, you know, if you average two kappa ellipses function, they are still kappa ellipses, right? So if F is kappa ellipses, G is kappa ellipses, F plus G over 2 is also kappa ellipses. And you can prove this by a simple triangle inequality. And you can do this for multiple functions, not only just two functions. You can do it for n functions. Okay, so suppose we have this, then now, so we also know that so suppose we know for every, so we already know that for every theta, right? So L hat theta minus, so suppose we condition on this event, right? So with some chance, you know, with a very high probability this happens, and suppose this happens, let's condition on this event. We want to prove that the same thing happens when you replace C by S. Right? So this means that if you have for every theta in, I guess I call it capital theta, but not S, right? Capital theta, the ball, you can find some theta 0 in C such that theta minus theta 0, L2 is less than epsilon. This is by the definition of epsilon cover. Right? C is epsilon cover of capital theta, that's why you have this. And then this implies that L theta minus L theta 0 is less than kappa times epsilon. This is by Lipschitzness. Right? So in some sense, you just use theta 0 as a reference point. Right? So what you finally care about is L hat theta minus L. Sorry, I guess you also know this. You don't only know this, you also know L hat theta minus L theta hat theta 0 is less than kappa times epsilon. This is also by Lipschitz. Okay, so now with this tool, you can, what eventually you want is you bound the difference between L hat theta and L theta, right? So, and we have seen this kind of triangle inequality, you know, this kind of like a manipulation already, right? Because, you know, eventually you care about the difference between L hat and L, but you use the theta 0, some reference points to kind of bridge them. So you do this decomposition, you say that this is L hat theta minus L hat theta 0 plus L hat theta 0 minus L theta 0 plus L theta 0 minus L theta. And now these two things are about differences between theta and theta 0. So this quantity is less than kappa times epsilon. And this quantity is also less than kappa times epsilon. And this quantity is less than epsilon. This is because theta 0 is in C, right? So we have already proved that for every theta in C, you know, L hat theta is close to L theta. So so that's why we got this 3 inequality, right? So in total, if you look at the absolute value, then you can do the triangle inequality to get the absolute value of the sum of the absolute value of each of them. You get 2 kappa times epsilon plus epsilon tilde. So sorry, this is epsilon tilde. Because recall that I use a different epsilon for the concentration, just so that I can tune this epsilon tilde eventually. Okay, so and if now it's the time to set epsilon to be epsilon tilde over 2 kappa, or maybe you can do it other way around, like epsilon tilde to be epsilon times 2 kappa. Then you balance, so that you balance these two error terms, so you get this is less than 2 epsilon tilde. Okay, so okay, all right. So now let's look at the let's go back to here, right? Because here there is something about the cover size we haven't dealt with, right? We have to plug in the right cover size. So And what is the cover size? So the cover size was, so log cover size, log C is equals to log 3b over epsilon to the power p. And I have already set epsilon to be epsilon tilde over 2 kappa. So I need to plug in that. So I get p, let's first get this, and then let's plug in the choice of epsilon tilde. So get p log 3b kappa epsilon tilde. And you can see that kappa is inside the log, so that's why it's somewhat not sensitive to the choice of kappa. And also epsilon tilde is also in the log, so which is also nice. And now we have to care about this failure probability, right? So we basically want to say that this is equals to something like delta, right? So we want to bound the failure probability to C exponential minus 2n epsilon tilde square, right? So this is something we want to bound. We want to show that this is small. Actually, in this case, I'm hoping to show that this is exponential minus p. Okay, so so how do we show this? And of course, it depends on what epsilon tilde is, right? So you need to choose the right epsilon tilde such that this is true, and then that's your final, basically your final bound. And just to get some intuition, so you're gonna see that this, the exact calculation of this is gonna be a little bit complicated. But just to get some intuition here, right? So suppose, so this is a heuristic which is not even technically correct, but it's approximately correct. So suppose, like optimistically, the log C is equals to P instead of P times log 3b over epsilon, 3b kappa over epsilon tilde. So suppose you just have P, you don't have the log term. Actually, this becomes a very simple calculation. So so what you got is that you got so basically, if you take the log of this desired inequality, you want that, let me see. If you take the log, you get log 2, which is not super important. You get log 2 times log C minus 2n epsilon tilde square. And suppose log C is equal to P, then you get P minus 2n epsilon square. And if you take epsilon tilde to be square root P over n, then you get this is equals to P minus 2P, right? Is equals to minus P, right? So which means that 2C exponential minus 2n epsilon square, if you take the exponential back, you get this is less than exponential minus P. So this is fundamentally how it works. Okay, but we did make this incorrect assumption that log C is equal to P, but this assumption is not very far, right? So it's only off by a log factor. So if you want to fix this, technically you need to deal with the log factor. It wouldn't change much, but it would introduce a little bit kind of like a complication. So I did have the calculation here. I'm just gonna basically write it down, but I don't really expect that you follow all of this. It took me like 1 hour to even figure out all the constants, so on and so forth. It's not super important. I think the intuition is already there. But let me just quickly write this just to say what you do formally. So if you suppose log C is equal, you only have this bound, right? So this is what we only have. This is 6b kappa over epsilon tilde. And then let's take epsilon tilde to be square root some constant times p over n times max. This epsilon tilde is actually the epsilon is the bound, is the final bound, right? So that's why you're gonna see kind of the same thing. and then final bound. And C0 is a sufficient large constant. C0 is a sufficient large constant, which we'll choose a bit later. So, and you plug in all of this, and you just again you look at the log of the inequalities we care about. The log of it is this, and you plug in this choice of C, you get P log 6b kappa over epsilon tilde minus 2n epsilon tilde square. And you somehow know that if you don't ignore this log, it's already work. It's just that if you have the log, you still have to deal with it. So you get something like P log. I'm not even sure whether I really have to write down all of this, but just in case some of you want to have this hardcore calculation. Right, so you get this, and then you somehow, I guess the first term becomes log 6b kappa. You expand the first term, square root C0p. I guess I decompose this into I'm decomposing the first term, 6 over C0p minus C0p log kappa bn. I guess the way that I always kind of think about this is that when you do the calculation, you always need to check with what happens if you don't have the log, right? So if you don't have the log, then this term is a large constant times p, and this term is p. So that's why it's nice. So eventually you can, if you take C0 to be something like 32, 36, I think you can show that this is bigger than this one, and this one I think this one is negative when p is large. And then you get this is less than minus p. I guess the exact calculation, there is some more detailed calculation in the notes, but it doesn't matter that much, right? So, so that's what we do. So then basically this is saying that if you take exponential, so you get of this inequality, you get 2c exponential minus 2n epsilon tilde square is less than 2 times exponential minus p. So this is our failure probability. So basically with this probability, with probability larger than 1 minus of e to the minus p, we'll have L hat theta minus L theta is less than 2 epsilon tilde, which is this thing that we wanted. I mean, not just not copy it again. So okay, cool. So that's the proof, and this proof is a little messy, and this is probably one of the reasons why if you open up a classical machine learning book, they typically don't show you this proof. So it's just because it's a little messy, but actually it's the reason why I always try to show this proof is that I feel like it's very intuitive, and it demonstrates what really is going on, and also this kind of things it's actually useful for many reasoning works. If you look at the technical low-level details, so the fancy Rademacher complexity thing that we are going to talk about next, they are very nice, but sometimes they don't apply, and you have to really use this. You go back to the most brute force way to think about it. Right. Okay. So maybe just a few quick comments about this proof. I guess if you really think about this, this is really saying that you have a generalization error, right? So it is less than the log of this excess risk, right? Up to constant factor, of course, plus epsilon to the k. So this part is from the finite hypothesis case, and this one comes from the. So this is not k, this is kappa. So this is the discretization error. And this is the finite hypothesis case. And in some sense, you are just trading off these two. And And what does it mean by trading off these two? It really means that what epsilon you choose, right? So this one depends on epsilon. So this one depends on epsilon, but it depends on epsilon in a very weak way because it depends on epsilon in a logarithmic. So that make it very easy to trade off this because you can pick epsilon to be quite small, so that this term becomes small and this term. This depends on, sorry, I think technically this should depend on log 1 over epsilon. Right, so the smaller the epsilon is, the better the second term, but the worse the first term. But the first term increases as epsilon goes to 0 very slowly. So that's why you pretty much can ignore the second term in some sense, just because you take epsilon to be very small so that the second term becomes negligible. And even when for those small epsilon, the first term is still reasonably bounded. And that's why you can make this trade-off really nice. But in some other cases, as we'll see in the later case, right, when you do the discretization, the first term wouldn't be as nice as this. It wouldn't be log 1 over epsilon. It would be something that goes to infinity as epsilon goes to 0 in a faster rate. Right? So it will probably, in the later case, sometimes this first term will be 1 over epsilon squared. Then the trade-off will become a little bit more tricky, and you have to be more careful about the trade-off. And finally, just for kind of like, this is a kind of probably all overview for just like a kind of like from some of the bird's eye view, right? So log h or p in this case, right? So or the p, you can think of this as complex measures. I guess I've mentioned this as well, right? So these are complex measures of the hypothesis class. So and the general like a phenomenon is always like you have a bigger h. It means that you need more samples. This is always like you have worse bound, so which means you need more samples to learn. And in some sense, the next 1 or 2 weeks, we are talking about a more accurate, I guess accurate may not be the right word, like a more fine-grained hypothesis, more fine-grained complex measure. So what is the right complex measure? There's no really a super decisive answer what's the right complex measure. In some sense, it's up to the theorem prover in some sense. So but we're gonna have a more fine-grained and more, in some sense, fundamental complex measure in the next few lectures, which is called Rademacher complexity, and you can use that to derive many of these bounds, in a more principled way. So, and in general, I think one of the important questions for especially in the somewhat classical statistical machine learning is to find out what's the right complex measure for your hypothesis class, right? So we're going to discuss, what does it really mean by right and wrong? Like there's no unique answer, right? So, but there are some kind of like, but this is kind of the central question, right? So you need a complex measure that really captures the fundamental complexity of this class. For example, if you have an infinite hypothesis class, right? So you shouldn't use log h. Log h is not really the fundamental complex measure for infinite hypothesis class. You probably should use dimensionality. Probably in the later of the course, we are going to see you can use the norm of your parameters as the complex measure. So and it does depend on the specific cases, and also sometimes depends on data. So this will be what we discuss in the next few weeks. I think this is a natural place to stop. Yeah. Okay, I think that's all for today.